During our team quiz, every student group had a different, and some of them were harder to build in Spartan than others. So I wanted to build a couple of the ones that weren't as intuitive or that you needed to use the inorganic menu for. Well, the first one was CO2. So carbon dioxide has carbon as a central atom with 2 oxygens on either side, and each of the bonds is a double bond. You'll see here on the organic menu that we don't have a carbon with 2 double bonds as an option. Although it is a formal charge of 0, it's not something that's commonly found in organic chemistry, so we need to go to the inorganic set. So I'm going to choose carbon here, and then I'm going to choose the electron domain geometry that I want. Okay, so here I've got a linear molecule that's going to have a double bond on either side to oxygen. I'm going to go back to my periodic table, choose oxygen. That oxygen is only going to have be bonded to one thing, okay? And then we should specify that those are double bonds. So I'm going to go down to the bottom of this menu, choose the double bond option, and then double click on each of these to make sure that they're double bonds. Now when I minimize the energy, you see that those bonds shortened up significantly, and that's because double bonds are shorter and stronger than single bonds. So let's move on and build another one. Another one that was complicated to build was nitrous oxide, or N2O. So we've got nitrogen, nitrogen, oxygen, where the nitrogens have a triple bond between them, and there's a nitrogen-oxygen single bond. This does minimize formal charges. It's not the best for either the oxygen or the central nitrogen, but the oxygen is more electronegative than nitrogen, so it's going to carry the -1 formal charge. In this case, okay, I need to get back to my periodic table, and so I'm going to click on any of these shapes, right? And then I get my periodic table back. I go to nitrogen. Nitrogen is my central atom, okay? And that's going to be connected to another nitrogen here, and also connected to an oxygen. Now here I definitely want to specify that the nitrogen-nitrogen bond is a triple bond, so I'm going to triple click or double click on that to make it a triple bond. And now when I minimize the energy, you can see that that triple bond is a lot shorter than even the double bond that we saw in carbon dioxide. Another molecule that some people had to build was the ammonium cation. And so if I build a new build window, ammonium cation has NH4+, which is a tetrahedral shape. If you go to the organic set, you'll notice that the tetrahedral shape for nitrogen is not there. These are typically going to give you the options for a formal charge of 0. Okay, so in this case, the nitrogen is not going to have a formal charge of 0. So we need to go to the inorganic set. We need to choose nitrogen and put it in that tetrahedral shape with 4 individual bonds. Okay, and now again, you can choose hydrogen and add it to each one of these bonds, or you can just minimize the energy. So I'm just going to minimize the energy. It's going to add my hydrogen atoms to each one of my nitrogen bonds. Okay. Remember, this is a cation, NH4+. And I'm just going to do the calculations quickly and show you what the electrostatic potential map looks like. Here, the total charge is 0. Because this is a cation, a +1 cation, you need to change it to 1. If you don't change it to 1, let me show you what happens. It's giving me a setup issue. You may or may not get this type of window. If you allow it to start the calculation, it will start the calculation, but it will tell you that it failed. And because you didn't tell it was a cation, and so it doesn't know what to do with that. So I'm going to set up the calculations again. Whoops. And I'm going to stay with PM3, but now I'm going to change this to a +1 cation. I'm going to submit that. And now it has been completed successfully. If we look at the electrostatic potential map now, you'll notice that it's all completely the darkest blue. And that means that it's all electron deficient. And hopefully that makes sense to you because it's a +1 cation. It has lost an entire electron. So the whole molecule is electron deficient, and that's why the surface is blue. So let's look at this a little more. If you are in that situation where you have a cation and your electrostatic potential map comes up this way, that's not super useful for telling where the electron density is in the molecule. Yes, the whole thing is deficient. Thank you. The electron density that is there, where is it? So if we go to the properties for the surface, we can see that that default color scale goes from a -200 to 200. The actual scale here is from 600 to about 800, so no wonder we're all completely blue. I'm going to reset that min and max, and that's going to give me a better idea of where electron density is. And you can see that most of that electron density is on the hydrogen atoms. Now that may not make sense because nitrogen is more electronegative than hydrogen. So why are the hydrogens electron rich and the nitrogen rich electron poor? Well, that has to do with the formal charges, right? We said that nitrogen, this whole molecule has lost an electron, and it turns out that it's lost it from the nitrogen. So if you calculate the formal charges for the nitrogen here, you're going to have a +1, and so that nitrogen is electron deficient, and the electron density that is present is on the hydrogen atoms.